agents, active inference agents, can deal well with fluctuating resources in data, in power consumption, in time latency.
This is a crucial difference. In LLMs, it's a pristine environment, but for these agents that go outside, you just need to act on the fly. You don't need to train on it. You just need to know how to avoid it.
So maybe the LLM can help process and generate hundreds or thousands of lines of code. So it's like that they can be used together, and they're kind of two complementary streams of synthetic intelligence.
It's as if rather than looking inside of a artificial neural network like black box model, you now can say, oh, this sentient agent, this artificial human being, so to speak, has beliefs, how they've associated what they're seeing in their environment with what they think is going on like in the world.
So if we can make LLMs Bayesian and completely distributed and self-organizing, then the LLMs may actually become low power.
I'm John Clippinger. I'm the host of First Principles First, and to give you a little background on what we're trying to do with this podcast. And that is that we're looking for a set of first principles, basically scientific principles to understand the nature of what we consider to be artificial intelligence, conscious agents. The whole thrust to have a principled understanding of what it means to have autonomous agents. And this ties into synthetic biology, physics, and neuroscience. We recently had, the last month or so, we had basically theoreticians. So we had Chris Fields. I'm not familiar with Chris' work on yeah, sure. And then we had Don Hoffman, and the two of them have worked together to specify CAs, conscious agents, traces of consciousness, that kind of thing. And then certainly Carl Friston, and then more recently Anil Seth. But we're now this session, I think we're really interested in understanding sort of like, okay, how do we go from the theory to the engineering and the implementation? And how do we really start to build things that scale, that reflect and embody the basic principles of active inference and Bayesian learning? And I think we have, and Daniel can certainly speak to this, and Andrew as well, there is a group, an active group at Active Inference is trying to extend and add to and learn as much as they can by RX Infer in order to apply it to different problem sets. So one of the things I'd like to do is not just the audience that is not just for those who are developers, so that's a key element, but to put in a broader context of what you're doing, say what is currently happening with large language models, with the sort of what people now regard as a sort of generative AI. What's the difference? And Bert, you talked about principled AI. You were one of the first to introduce that term, from what I can tell. And so it's, even the Gartner groups picked it up. So there you go. And so what is the difference, and how might it live in conjunction with the sort of the large language models, the transformer models? What might be the symbiosis there? And then how do you see this being extended into a broader ecosystem? And then I think we have an opportunity to delve more deeply into what it is, what you're doing, and how it works, and they have the questions around it. Does that make sense to you? Is that?
Yeah, I think so. I think so. I mean, okay. So first, maybe I should just first tell a little background about our group, right, where we come from.
Right.
So I will keep it short, but my own background is as an electrical engineer, as a hearing aid designer, and hearing aids have this is a product that goes out in the field. And usually people are very happy when they leave the dispenser, but something always happens. The world is not as expected, right? So the hearing aid has to be updated in the field, but the designers of this hearing aid, the engineer and the audiologist, they're never there when something happens. When you're in a restaurant and you cannot understand your conversation partner. So about 10 years ago, I started thinking about, how can we make the hearing aid itself responsible, and that for updating itself, because the patient is usually not able to manipulate algorithms, right? So the hearing aid itself should be not an algorithm, but it should be an agent where the algorithm is sort of like a side effect. But the first responsibility of the agent is to survive, to not end up in the drawer. And so that led, I connected that. I mean, by very just some coincidence, I read something about Carl Friston and the free energy principle, because I'd never heard of it about 10 years ago. But I was really hooked on it immediately, and I didn't understand it, of course. But for the last 10 years, I mean, like 2 years later, in 2014, so 10 years ago, I started a group here at the University in Eindhoven in the Netherlands, and our goal is to basically to implement free energy minimization fast enough to design these agents, not just for hearing aids, but for everything else, right? And so Dmitry, who's also in the call, is the main designer and an engineer of ArcSinfer, which is our current toolbox. So where does it differ from large language models? I think agents, active inference agents, can deal well, at least the way we try to implement it, they can deal well with fluctuating resources in data, in power consumption, in time latency. If you meet a car, it depends on the speed of the car, how fast you need to react. So the fact that the amount of computation and the amount of that you can do in amount of time fluctuates all the time is very characteristic for the agents that we try to design. We want to get a good enough answer given the resources. And I think usually an LMN currently still operates in the same way a week from now, right? And because it just expects to have the same resources available. But an agent in the field may not have the same resources available. There may be a lot of missing observations. There may be less power because I don't have to care about one car, but there's 3 cars around me. Those kinds of things. So that's, I think, where is the main difference. And I'll leave it at that for now.
Well, can I just probe that a little bit
Yeah.
more? Because I think that's a profound difference. I mean, and I think that so the consequence of that is in your material is that you can run on you don't have the computational resources that are required for large language models. They update themselves, they're adaptive, and they have an internal representation correct me if I'm wrong, of themselves and what they're trying to achieve, and so they can. And this whole idea of having internal representations of your internal states and your external states and how they work together, I think is a really a key element of this. And then how it's able to adjust those relationships and update those relationships over time under fluctuating conditions is not something you see in even near in the LLMs. Nor I think there is this whole move towards agentive architectures. You can see that with things like Crew AI and others, which themselves are really not. They're sort of a specialized roles. They don't have their own internal representation. They don't have, I mean, in say in a Friston or because Field says they don't have a self. They don't have a sense of who they, what their boundary conditions are relative to other things. Is that am I?
Yeah, I think.
Explaining or putting words in your mouth or
No, I think this is correct. So I think it has to do also with I mean, in the real, we're going now to the realization. How do you realize these agents that have to deal with fluctuating resources? I mean, it means you have to do distributed computing, so distributed across resources. Like in this, and what I mean by that is that, okay, a soccer team here in Europe has 11 players, but if one player goes out, sometimes a team of 10 also beats a team of 11. And you can also play with 9 against 11 temporarily, right? And so, whereas in an LMM, I think if one transistor fails, probably the whole system may actually break down, right? And so this distributed computer gives you the robustness to deal with, well, when some agent falls away. Or when I have a little bit less time. The fact that the entire process is free energy minimization, and free energy minimization is bit by bit by bit by bit by bit in the terms of we pass messages. Also means you can stop at any time and you have a result. Yeah, the longer you wait, you get a better result, but you can always interrupt. You're not in the middle of some loop of some algorithm that that hasn't ended yet. You always have a result. And so you have distributed processing over space and over time I believe that's in the implementation that we try to do in RxInfer. And that means you can always interrupt, you can lose some agents, some resources, and we have a result. Even that may not be the optimal result, but there is a result, right?
Well, that's sort of a biological model. I mean, you could that's sort of that's true of biology too. I mean, and so would you say that as well as it has certain biomimetic characteristics and being able to recover that
Well,
way?
yes, or at least, but it's very important for engineering to have robustness, right? Particularly for systems that go out in the field in the weather conditions, right? Yeah, and that's what basically what our toolbox is like. This has by itself, I mean, there's good engineering reasons for it, aside from the free energy principle and active inference, right? There's just from an engineering viewpoint, you want to have these kinds of robustness to losing some resources or having fluctuated or dealing with fluctuating resources and still have an answer, right?
I can also add a little bit to the question,
Sure.
right? Like, hey, hi everyone, Dmitry here, the main architect of RxInfer. So this is an interesting question, right? About like how do we differ from LLMs? For me, Bert is right, but I can also add to the fact that so LLMs, in my opinion, maybe some will disagree, but they are basically essentially a very, very smart compression algorithm, right? Like they take a huge amount of data, they somehow process it such that you can query it later on. So, and they require like enormous amount of data. They train on the entire internet, right? But so for indeed for agents that want to kind of just go out and explore in the environment, they live in this kind of interactive environment, very uncertain, where certain events may occur only once. For example, you may go somewhere, right, and you see a bump, and then you just go around this bump, and then you go straight, and you will never ever see this bump again. So, just doesn't make sense to train your system to avoid this bump, because this bump will never ever happen again to you, right? This kind of another this is a crucial difference. In LLMs, it's a pristine environment, but for these agents that go outside, you just need to act on the fly. You don't need to train on this. You just need to know how to avoid it instead of just
Yeah, so you need to do reasoning rather than just getting from memory, right? You need to
Correct.
you need to do rational, proper reasoning when you hit events that only hit once ever.
Also, but you can also specify. So one of the things that we were interested in is how you can specify a model and to what extent you and how you specify a model and this whole idea of not necessarily having something that is imperative. Now that you're actually maybe have something that's a loosely defined set of goals or outcomes within a particular range that you want something to discover. I mean, and I guess this gets into expected free energy minimization capabilities, and to the extent to which you're able to support that, and that's part of your the design interests. I would be interested in that.
Yeah. I mean, we're not done with RxInfer, right?
No, I mean, yeah.
I mean, we're far from done because I mean, truth be told, I mean, it's very difficult to design an active inference agent. You have to know a lot at the moment. There's few people that can do it, and I have graduate students here. They cannot do it, right? They're also not enthusiastic when I let them work with RxInfer because probabilistic modeling is very hard to wrap your head around. So we have to build lots in the future, lots and lots of tools, engineering tools for debugging, for visualization, to make it easy, maybe live coding kind of thing, to make it easy for researchers and students and everybody to design agents, even though you may not be the world's expert in probabilistic modeling or in Julia, which is the language that we use, right? Because now there's almost nobody who actually wants to work with Infer. And yeah, so there's a whole lot, big road ahead. It's tough for us, I mean, I'll be frank with that, to develop that because we are an academic lab. I mean, we don't get PhDs for building an engineering and for building a visualization tool, right? Or for building a debugger. It's hard to get a PhD for that. So we're not in an optimal environment to develop Infer all the way out. But I hope we make it open source, and I hope, yeah, that we're going to have a bigger community developing.
That's part of what we're
Infer.
trying to achieve, actually, in this call
Yeah,
too.
yeah.
And I know Daniel's got a lot of ideas on this. But how you're, I mean, being able to maybe have a tech tree or something to identify the different things that people need to contribute to in order to create this whole effect. And there are people that are willing to contribute to a debugger or visualization or other aspects, and others can focus on the core, the core, and that is, I think, part of our interest here is to see how we can assemble different groups of people who have different skill sets to contribute to this overall effort and coordinate ourselves around that. I mean, and also I think one of the things we're discussing is with Daniel is how do you might get some kind of funding so you could actually have some funding mechanism that the bounty-based funding. They said, gee, we really want to have this done. Can we? Would someone be willing to invent? Would someone be willing to sponsor that kind of thing? And then that goes into the repository, and so we start building on this. And I also think there are certain kind of use cases that would get people motivated is actually the application, and that. And so when you think, well, here's a certain kind of data set that you can work with, that this, if you apply this approach, you're going to succeed in ways you never thought before. You can do things otherwise, and so we have the API to those kind of data sets, and so identify those people who are coming in to make it available to apply the engine to that. So that's part of what we're trying to establish here, and what might be those sets of partitioning out the work of different folks in order to make this ecosystem evolve. I'm sure Daniel's got some ideas on this.
Sure. Thank you. Well, greetings, everyone. Watching from the side earlier on as a PhD student and continuing on through the work with the Active Inference Institute and Andrew, I've seen Bert's group do incredible things earlier on in developing the relationship between the Bayesian graph and a kind of isomorphic cousin, the Forney factor graph, that gave a schedule to the messages that were being passed. Up until the reactive implementation, that schedule was still kind of like a metronome. And so it's been kind of like seeing the training wheels come off on a distributed system with the reactivity, because there is a certain reactivity of an agent in a niche, even with a metronome. Like new observation comes in, and it is a reactive type output when the action then comes out. And that kind of like observation in, action selection out is the basis of all kinds of training environments like OpenAI's Gym. And then for that to be relaxed, it's been a awesome journey, and to see many people participate in open source. You mentioned specifying a model, John, and about how the specification of the active inference model has been largely imperative, which is to say, it's in terms of the programmer's semantics. Like, take my variable 1 and do this to 1, then take my variable 2 and do this. What the Bayes graph had always been pointing towards would be, what if the model's semantics were the agent's semantics? So it wasn't just the hearing aid programmers' concerns about how big this variable is and which order to do things in, but it actually reflected the semantics of the environment. And so now with the at model type specification and a lot of these tools and abstraction layers that RxInfer is providing, that is moving closer to happening. So there's more avenues to explore, but I'll just leave it there for now.
That's
I can
fantastic.
also add a little bit to the discussion. So basically, I'm super agree that we need to develop some sort of like a platform for new developers to be able to express their ideas in terms of the models, right? Because in a sense, the model quest is a very difficult quest. Like, which kind of a model do we use? But we will find it through this process of experimentation, right? Like, we will try different models, 99% of them will fail, that's perfectly fine. But if we can make this loop faster of experimentation, right? So RxInfer basically tries to make this loop faster by providing model macro, by providing API to run inference, etc. But it's still challenging, right? You still need to have like some knowledge to work with that. And if we take a look on LLMs, for example, right? They have a really good platform for experimentation, right? So you actually don't need to do much. You can just download like different LLMs in a matter of like minutes if you have a good internet, right? And you can start experimenting. It's all like in the cloud, and people can upload their own models. They even have like leaderboards, right? They have benchmarks. So it doesn't matter that like 90% of LLMs are like they don't work, because through this process you can find those 10% that actually work. So I think that the next step in this journey is to develop this kind of a platform for people to be able to interact with it. So for example, now we have this project with Active Inference Institute, right, that will help to visualize the model. All right, so like what kind of model we actually are working with. And then it will give maybe some insight. Maybe if something doesn't work, then you can display some sort of like quantities on this visualization, and they will kind of hint you why it didn't work. Maybe this particular node didn't play well with the environment or something like that. But this is not existent yet. So I think this is the direction that kind of we should be pursuing, the tooling around RxInfer. To make it easier to work with.
Do you have a sense of what those say a minimum set of, you was talking about having a platform, what the minimum set of things would need to be in place, or you like to put in place in order to do that, and how that, some ideas of how that might come into pass, and how we activate a community around this?
So there are things, for example, obvious as I mentioned, visualization. What kind of a model do we work with? Because this is extremely super important, because we actually work with the graphs, right? We have the visual framework for the underlying kind of algorithm. So we need to be able to understand what is happening inside of this graph. Because currently, like, and also because we now added this reactive layer, it's actually quite difficult to debug what is happening inside. It's like these messages are flowing around, new posteriors, like new free energy spikes, and this can be all asynchronous. You have all of this data coming from different sources. This is extremely difficult to debug, even for me, right? Like I designed it, but like really sometimes it's just too difficult. So this visualization platform coupled with debugger, that I think this is already will be a very huge improvement. Another thing is that this is mostly for like core part, maybe for like core developers. But okay, like we can define some model and we can run inference. Maybe we don't visualize it for now, but inference may fail. Maybe for non-obvious reasons for a user. But there is already a solution for this, right? There is already a solution, maybe in the documentation. Maybe a user just didn't know about that there is a fix for this particular problem for the inference. So we can kind of give a hint. So what currently is happening in RxInfer is we just throw an error, and this is a very huge Julia stack trace with like lots of errors, and we as developers, we actually understand what is happening, and we know what to do to resolve it, right? But external users, they are most of the time they're overwhelmed by these huge stack traces, and they are lost. Like, but like for some errors, we have some hints like what to do, but they may be a bit vague. But for some errors, like it's like there is no hint. Basically, you just need to know what to do. So
So yeah, what I'm thinking about is if we have very large models, eventually, I mean, nowadays we still work with smaller models, right? 10, maybe 50, 60 nodes or so. But let's say we build models with a million nodes, like try to build real big systems, right? Um, since the only ongoing, and each node is minimizing its free energy, right? Just like what a brain does, and it does it just by sending messages and receiving messages and sending messages. But this free energy process is completely distributed over the graph now. You can do imaging. What we could do is do a heat map over this network from green to red and show which agents are not performing, which agents are not minimizing their free, are keep making the wrong predictions. And so hopefully by creating an image over these million nodes, you can see, hey, here in the right corner, this part of the graph, this part of the model is not working. Here is where I need to maybe manually start thinking about what I'm doing wrong. So this is also a debugger that could work on a larger scale by just like a brain. You do imaging and you see what's, you look at the color of the plot, which agent, because the only thing they're supposed to do is minimizing their prediction errors. So we can measure that and we can show it on hopefully on on just an animation, a heat map. So that's what I think if we go to really big systems.
I'll add another piece on the application pipeline or pathway, having seen this in different languages over the years. Dmitry and Bert, they're coming back from the engine room, and those are very great and true points. And one of the first jumps to get to an application in a certain system of interest or a domain is to get whatever it is, the data and the unobservables and the action control possibilities out there into this app model block. What's super cool about the app model block that makes RxInfer active inference models different than even other implementations is the app model block looks a lot like the equations of the joint distribution in plain text. So that's really awesome. First jump is to get from what's out there, what are the sensors, what are the unobservables, what are the affordances and all of this to the app model block. So that relates to learning and applying the active inference ontology in a domain. Then that is kind of like this boundary artifact or eye of the needle, because now what needs to be specified is all of the rules and heuristics by which messages are passed. Because if you just specify an app model block, it's kind of like a car that's turned off. So then packages like rxenvironments.jl and other kinds of ways of putting the actual like spin and the kickoff there. And so I think if there can be better scaffolding to go from an arbitrary system of interest to an app model block, then from an app model block and all of its accompanying visualizations, and adding in the sort of rule sets for, okay, here's where you drop the pinball in, and here's what happens when this happens, and those kinds of rules. And hopefully everything else just starts humming under the hood. So it's a few jumps, but that starts getting at, well, where are we looking more at things like workshops and domain guides and ontological concordance tables, and where are we looking more into like Julia routines and other kinds of debugging traces?
yeah, it's a good point. Actually, indeed, I think like model macro is like allows you to write basically many things, right? But like I mean, it's very flexible in terms of model specification, graph specification. But maybe for like active inference agents, we don't really need that kind of power, that kind of flexibility, because they really, they are kind of still state space models in a sense. They have some kind of a properties, like agent has a state essentially that progresses in time. Agent has kind of an action that they can or maybe they will not do. So there are like this kind of two entities already, right? So in this model macro, there should be a state, there should be an action. They may be some other properties of an agent that do not change over time. So it's not a state, but just a property like a mass or engine power or something like this. So there are already kind of, there are some constraints already on how do we want to specify these agents, right? And it's usually like we'll just progress over time. So maybe we can just take indeed an application and directly even bypass model macro and directly create this all the internal data structure that are needed to run inference, right? Because model macro is again like for experimentation, but if we know the model structure, we can basically just use the internal API to just generate the graph itself. So that can be indeed a direction, and then we can connect this kind of agents to NRX environments.jl, for example, to test them.
Yeah, there's still a lot to do.
But we may get a number of other people to help do it. I mean, that's
Yeah, no, that's
that's what
fantastic.
there may be ways of partitioning the work into those. So the work correct me if I'm wrong, but what I'm hearing is yes, there's certain ways in which you want to develop the core, but there may be things in the interim that you can do that have application domain opportunities, and that therefore people, if you can do that, then you can demonstrate the value of it and get contributions coming in. And from what I'm hearing you say, at least some of the examples that I'm thinking about, that they may lend themselves to that, and that in working with some of the work that you've done, Daniel, in terms of being able to use cursor and being able to access, and this is also the work that Axel Constant is doing, is sort of access a large language model to generate a vector of an application and then have that fuel the model. And this is where they come together. I think that's pretty dramatic, and it's sort of, to me, it shows the limitations of the LLMs and exhibits the value of and so we're looking at the legal domain. I think there are other domains in the economics domains where you can actually show that. There's also a lot of data that one can get right away. I work with a group that is demographic data and geospatial data and like that in a format. Because what I'm hearing, and correct me if I'm wrong, maybe, but I think just the ability in the example that you use with the drone, and basically, okay, you have something, you have a model basically of its energy consumption, you have a model of movement, and you can put these things together, compose them, and they can actually work in unity. And that's a real time, and you're dealing with something in real time, whereas a lot of these examples aren't necessarily real time. That I think you can show some really compelling results that are currently limitations of the existing LLMs. And so I think what we're trying and working with Active Inference Institute is to identify some of those domains and have some hackathons and involve people to do a proof of concept to illustrate that. And that's sort of on our agenda.
Yeah, I think that's fantastic. I mean, like realistically, the group that I have here in Eindhoven is a group of PhD students in electrical engineering. They're very well suited to make, let's say, the message passing more efficient, to work on the math, to write a dissertation about it, to test out different optimization technologies. But to make a system usable by 1,000, 10,000 people is not what you do for your PhD. So that's why we need the help, right? Yeah.
Exactly. Deanna, you can comment on that. I mean, you're doing some work on the visualization, the VisGraph, and things like that. And yeah.
Yeah, it makes me think about the generative AI contributing a certain fluency, like being able to output a given expression in many human languages or to translate semantics across programs. So that kind of fluency, and then the Bayesian symbolic and semantic, counterfactual, all of these more structured reasoning processes that they are kind of like a skeleton and a flesh because you can have a certain semantics that's projected down to a Bayesian graph and then use it to kind of like refract like a prism into like different human languages to explain it in different settings. So I think finding out new ways that those pieces can fit together. Another example, like you brought up with using augmented coding, is like meta programming in RxInfer. So as we build up libraries of examples of working RxInfer programs, the patterns in the syntax of those programs become something that we can leverage into using the LLM to recompose and recompile a new RxInfer program that when that is actually, when you hit play on that, it is all RxInfer, but maybe the LLM can help process and generate hundreds or thousands of lines of code. So it's like that they can be used together and they're kind of two complementary streams of synthetic intelligence. And then also when people are studying distillation or interpretability in large models, they're taking models that have a preset multi-billion parameter structure. It's like the quote, like, give me 5 parameters and I'll outline an elephant. And then with the sixth one, I'll make the trunk wiggle. That's only 6. Of course, that's a joke. But when you get into the billions and the big data, and then the challenge becomes how do you project it back down for interpretability? With a Bayes graph as a human interpretable artifact, we're working towards semantics, but from a kind of grounding that's smaller, and then figuring out how to bring that into the fluency, because we're not going to be able to capture like a natural language fluency in a 10 node Bayes graph, but we might be able to have like 10 top level summaries of an organization that can then be generated into multiple reports. So there's a lot of ways to combine the two.
Yeah, for sure. Yeah, I think just to kind of elaborate more on that, one reason why Bayesian inference is not used, where it's not widely spread. I mean, people kind of agree that probabilistic reasoning is a proper way of dealing with uncertainty, but the big thing is the computational load, and that's a bit odd because, well, the brain actually does variance minimization, and it's very, very cheap. The reason why it can be cheap is because this resource issue also goes the other way around, in the sense that sometimes or very often I don't need 11 players to fix. But when I'm in offense, my defenders are just standing around in the back. And when I'm in defense, my offensive players. So at any point in time, I don't need the full team playing, and I can actually. So a Bayesian system, when it's distributed, can also decide, I'm just going to use I'm not going to use all my resources, I'm just going to use little resources. And this, I think, may actually, in the future, be the breakthrough for LMMs. So if we can make LMMs Bayesian and completely distributed and self-organizing, then the LMMs may actually become low power, right? Because now they always do the same thing. But when I learn how to how to drive a car in the beginning, my model makes all the prediction errors, and I need all my attention, and all my resources goes to learning how to drive. Once I know how to drive, and my model is very good, I mean, I don't even know how I got home, right? I mean, there's there's almost no computation going on because all your predictions are correct. So over time, as the system trains, it should use fewer and fewer computational resources, and this would you can do this in RX Infer, and I hope at some point in the longer future to infiltrate the LMM community and do that to LMMs. So then the difference between the two may not be so big, because then also LMMs can actually train in the field, because they won't need all the resources, right? They only need the resources that they need at a particular time. Yeah, in the end, I think it's just because we do Bayesian reasoning that we can be computationally cheap. It's right, rather than a big hindrance to doing good computation. I think Bayesian computations in the long run will be advantageous if you want to do really cheap AI.
But that's a big issue for LLMs. I mean,
Yeah,
the energy
yeah.
consumption is a huge issue. I mean, not just in terms of cost, but also ecological issues. And I think that
It is. It is.
recognized.
And if you do not have internally any representation of uncertainties, then what can you cut away? You can't cut away. You cannot stop computing, right? You may be far too accurate, right, already, but you keep computing because you don't know that, right? Everything
Absolutely.
is 24 bits or 30 bits or whatever you do, but you want to stop when you're accurate enough. When you solve your problem, you want to stop, right? So
Uh,
this is what you can do with very distributed Bayesian technology that's reactive, and I don't see how you do that if you do not have a probabilistic model.
I don't think there's any argument here.
Okay. Well, we haven't solved that either, right? But I think it's the way forward to making very large systems computationally cheap. To go the Bayesian way, do it distributed, and only send you messages like when you expect to minimize free energy.
On that, actually, Andrew, what would you say? How was it conveying and dealing with questions when you were in the social setting? What are the benefits of having a probabilistic model at all like this? And like, how does this compare to other ways that people have seen distributed simulation in the social setting?
Sure. Yeah. Hi everyone. I'm Andrew. Yeah, I just want to quickly say, by the way, really interesting work with RX Infer. I've been, joining the institute's group that's dedicated to that over the past several months. So I've been very busy the past couple months, and so coming back, it's just wow. There's really nice things going on. So very happy to actually meet you. So I'm actually coming at this from a very different angle. I have a background in the social sciences and kind of cognitive science, not so much the engineering. But I am also a programmer, and so I've done some work with MATLAB and the kind of tools that Carl Friston developed, over the past couple decades, and then switched to Python. A lot of interesting developments going on in there, but part of why I'm so interested in RX Infer is in part because all these kind of optimization issues with those two previous sets of tools I mentioned that I'm starting to see are now possible to overcome using the Julia language and then RX Infer, setting up RX environments as a means of simulating agents and environments and kind of connecting the dots. So a couple months ago I did a conference and I kind of talked to social scientists about how they might apply active inference. They kind of work in this field called agent-based modeling, which of course is so general that it's not just a social sciences thing whatsoever, but the tools they're using are a little I don't want to say outdated, but there are very particular views of how to go about doing agent-based modeling. Some folks have slowly moved into reinforcement learning, but it's there's no free energy minimization. There's no point of reference to cognitive science. It's usually kind of an ad hoc post-interpretation. It's like first you make the agent, and then afterward you say, oh, it's as if it's planning, or it's as if it's doing this, but you don't have a first principles perspective. Yeah, and that's why I think finding a way of both optimizing the tools, which is what you all are doing, while also starting with, these kind of cognitive principles, as opposed to post hoc, like adding them in or wishing that they're there. I think that's the value to all of this in many ways. And so with probabilistic representations, for example, so with agent-based modeling, you're and by the way, again, fascinating to hear about how this starts with developing hearing aids, because in a very social science different world, where we're attempting to model something like sentient human beings, as if you might move in that direction and exhibit natural intelligence. And so that could be applied in the social sciences by saying, oh, this more closely imitates or even recreates the behavior of actual human beings, at least at particular levels, starting at more of like a kind of micro or neuronal foundation. With having probabilistic representations, it's as if rather than looking inside of a artificial neural network like black box model, you now can say, oh, this sentient agent, this artificial human being, so to speak, has beliefs, how they've associated what they're seeing in their environment with what they think is going on, like in the world, and like kind of hidden or latent states in the world. And so now you have a whole set of interpretable parameters for trying to simulate something like social behavior or even economic behavior. There's been some interesting discussions that I've had with John and others about potentially actually trying to recreate like an artificial economy using sentient agents. And this has been done before, but not minus the sentient part, right? It's usually kind of pre-programmed rules about assumptions about human behavior. And now we're kind of like almost reinventing that with active inference. So I appreciate the probabilistic representations. I appreciate the kind of interpretability that can be extracted from this, at least in the kind of social science setting. But I don't want to overspeak.
Just to build on that point, because I'm sort of the applications interested I'm in is more sort of social, cognitive, collective, cognitive, economic, institutional, organizational. I mean, just to think about the notion of a firm, what's a business, is a sentient thing, and one of the things I really like about with your approach is you're able to, and you see it in your example of the drone, is that you have calculations tied to the physics of its movement and what's in its world, but also its cost of energy. So you're able to recognize the kind of adjustments and trade-offs that living things do in order to actually achieve achieve who they are, maintain their self-evidence themselves within a set of constraints. You can't do that with any other method in economics or so the social sciences. It doesn't exist. So that to me is really fascinating, that you can take these different generative models and compose them into a larger model that tries to make those adjustments. And I think that's foundational to a new way of looking at organizations. And so what is a firm? And well, a firm has a sense of it's a theory, a hypothesis of what it is, and whether it can survive under different kind of constraints. And so there's a lot of data out there that one can get. There's a ton of financial data. There's a ton of economic data, and even in behavioral data. So I think this is a very powerful way of looking at things that I think opens up insights into which people just didn't think were there, could possible. I may be getting my skis
No,
on
absolutely.
this. Right.
No, absolutely. I totally agree. And I mean, this is one of the things that I really like about this community up to this point. That I mean, even in this call, right? I mean, Andrew, you say you're a social scientist. I believe you're a biologist, Daniel, or a zoologist, right? And we are electrical engineers, and Dmitry.
Many things you can.
So and everybody comes with their own fascinating story to seek some deeper layers on what we are working on. So in the end, we're all going to, I think, end up as physicists. But But yeah, no, but it's interesting that everybody has an interesting story. What why they came to this field? Huh? I mean, I just read today there is next in 2 weeks the international workshop on active inference is going to be held in Oxford. And last year, I think there were 80 participants. So the year before, like 40, and this year 120. So it's slowly growing, right? And they had to, as far as I know, they had to cap it now at 120 because, well, this is the capacity. But it's still very small, right? When I went to NeurIPS, which was in the early days called NIPS in 1990, there were 60 participants at NIPS, and it felt a bit like this, right? But this was in 1990. This is 30 years ago, or 35, 34 years ago, right? So just to show how early we are still in this field, right?
It's true. But in my career, I've been at, it's, where you start out with 15 people, and then, but I mean, and then
Yeah,
some, and things happen very fast. I mean, I was involved in the early ideas around non-fungible tokens, and before they became, and I remember we had this in New York, and this is only 4 years ago, 3 or 4 years ago, and there were
yeah.
more speakers than there was audience. I mean, it was like, and then and then 3 years later, you had 15,000 people, and it went crazy. I don't think this lends it to that, but I do think there's something fundamental that will be discovered that will trigger this suddenly. The light will go off, and people will say, this deals with the problems that we see in large language models. And I think what'll augment that is being able to have some kind of use case. And if I understand what Dmitry is saying, is that when maybe even what we have right now is sufficient to actually work on some of those problems and illustrate that. And I think that would make a lot of sense for all of us to identify that.
Maybe one kind of general point is part of the success of reinforcement learning and reward is that it can apply to anything because you can write any kind of reward function. In active inference, we have the pragmatic value, which is kind of aligned with reward and also epistemic value. And so when we think about self-evidencing, also that is equally to more general because for different kinds of things, they're going to self-evidence differently. So it'd be like before reinforcement learning was finding grounding and application in domains, it'd be like, okay, it sounds kind of interesting that you can propose this ancillary secondary function, but then how do we design that reward function so that it stabilizes the motor or so that it does well on trading? And then as those kinds of ways to design these ancillary reward functions became developed and all these ways to optimize on them and train on them, then traction started to improve. Here, we've kind of stripped that second layer or never really proposed it because rather than trying to optimize against some kind of secondary proposed function, it's just happening directly on the path of least action of the model's parameters. And then the question becomes, well, then how do you set up the model and its parameters and the way that it intakes and outputs so that the way that it actually isn't just like a plane that crashes? And so again, how do we figure out to process data and to make systems that maybe do we need to grow from a small plane into a larger plane? And then could that larger plane's parameters be cloned? Or what are all these other kinds of moves that are possible, analogous to how reward functions can become trained in any domain? How do we make it so that the thing itself can be trained and sentient or however it is in different domains?
I think
I also agree.
go
Yeah.
go ahead,
I also
Dimitri.
agree. It's interesting because we actually started this discussion like how to onboard people, and we are again into this discussion. And I will be very again pragmatic, and I think the way to invite more people to grow the community is to provide again better tooling. And I think also like reinforcement learning, a part of its success is that they actually gave really good tooling for people to experiment, right? So tooling is actually the key because, for example, we cannot gather like 15,000 PhD students on a conference, right? There's not that many PhD students just to come. Like we need to invite more people, like master students, bachelor students, like just the regular people who maybe not even like they've never heard about like free energy, but they want to like program their drone, you know, and they just Google like, okay, there is Ericsson Infer, okay, I can download it, and okay, it works, it's really nice. Because like actually I have like some side project, right, and I needed to implement some interface like in the browser, right, and I really don't know how it works. Like I really like I just downloaded some library, there is a documentation, it's like, okay, there is a button, okay, I can download the button, I can put it, works really nice. I can download the drop down menu, works super nice. Really have no idea how it works, but it works, and it feels great when you just download this component. You just put it on your interface and it immediately works, and all the styling is there. You don't have to think about it. So this is the key, like, because I've been sold on this, right? Like it was like super cool. So the key to invite more people is to have this kind of feeling. So they download Ericsson Infer. It's like, okay, there is a model for a drone or something. I can download it, okay, and it works. You know, this kind of magic is the key. And many tools they went through it. Also LLMs, they exactly the same experience. You just download one library, this transformers, which is actually quite old, right, from like 2017 or something. You just download it, you type a little bit in the documentation, okay, there is like a certain call you need to make, and then it just trains. Maybe you don't know how like this linear algebra works under the hood. You don't know how like GPUs work, and maybe you don't even care. The only thing that you care, you like to solve a problem, like application. So this is my point of view on this, how to invite more people.
Yeah, we need to work on a higher level, right? We need to invite people to work on a higher level. If you want to design an agent for a vacuum cleaner that cleans your house, then it needs an eye, and it needs actions for direction, and if you do this, you don't want people to do this from scratch. You just want to say, okay, here's a camera, and there's a whole module, a generative model behind it that works, right? It creates a representation of the world, a visual representation. And here is an actuator with a generative model for the actuator, right? And so you cannot expect from people to start building every time everything from scratch. You just want stuff that works, actuators, sensors, and generative models for these sensors and actuators. You just want to and you maybe if you want to start with a crappy vacuum cleaner, right, and just try to improve it. We want to reuse stuff that kind of works, and then start building, making it better.
To give an analogy with the model macro, right? So basically now people, they need to do it from scratch, essentially. Like they need to build their own model macro every time, again and again. And you can kind of go to a really advanced examples of that if you know what you're doing. You can create a very large models. They work really nicely. You can fix all the errors from Julia's side, and the inference will be great. But we cannot expect people to do that. So also a part of like last year was a really big project from another PhD student of ours to make like nested modeling possible. So now it is possible to use a model within a model, like, or within a model. The hierarchy is like basically.
You can do that. You can do
Yeah.
that.
So we can do that, and it's merged, and it's like an Ericsson Infer already, right? And we've tested. So basically, the idea behind that was exactly, so someone can define a model for a certain part, for like a video processing or audio processing or whatever, and you can just use it, right? Just plug it in. Someone like a super smart person has designed this model for you.
Yes.
You just downloaded it, and it just works. So this is kind of the idea. Which is like still in very early, because this submodels, they were merged like less than half a year ago, I guess. So we're still experimenting, but this is kind of the way works.
But in principle, it works, and that means we can build nested models, right? A model becomes a node, and a network becomes another node, and we can start building nested models this way.
I
Yeah.
thought about it. I didn't know that that was that mature. That's huge.
Yeah, yeah, yeah.
I mean, I mean, so if I'm interested in organizations and organizational structures and as nested rather than as the flexible, that's a whole different model of organization. So I can represent different functions within an organization, within a firm, as nested models. That and so one of the things I was thinking about is an initial application is being able to people could create their own little businesses as nested models, and you get access to the data set. You create a hypothesis of like the performa of what that company would be. That's their hypothesis, and then you let it loose and try to see how it adapts to a different kind of environment. That and if it succeeds, then you have a successful entity, and it knows how to conserve energy, it knows how to get access to its resources, so it knows how to keep itself alive. But it's a very different model than what we have right now is the firm. It's a very different concept, and it's much richer. So I think that's extremely powerful. I'm weighing in here. I'm saying, yes, I mean, I pushed this rock around for many years, and so, and and you hit a certain wall, and it comes tumbling back on you. And one of those was the nested representation. The other was the conservation, the tying energy conservation into exploration. So if I could do some of those, then I think that is transformative. I mean, the notion of the firm, as it's now understood in economics and organization, and Andrew, correct me if I'm wrong, is really sort of a primitive artifact of the Industrial Revolution. It's very static. It's not, and so it has all these issues. But this is, if this is sort of doable in a simple form, I'm quite energized by being able to pursue that.
I mean, just spinning out the tech tree kind of sketch, it's like all these kinds of firm operations, like mitosis, a split, and merge, fuse, pivot, learn, explore, exploit, all those kinds of operations. There could be a sandbox, nested models, have a cognitive model of an employee. First, all they do is on dimension one. And then this is kind of maybe to the purpose of the podcast, that's a benefit of first principles is it's not like building a teetering tower where it's like, will what happens on the 50th floor be influenced because we made some kind of interesting semantic thing on the 20th floor? This is kind of like building it all laterally from the ground. So then it's like they can show, okay, each node minimizes free energy. Okay, development 2, nodes can be nested. Then it isn't that 5 layers of nesting is a specific advance. Those 2 advances, being first principle, help go and generalize because the motifs are already there. So if we can kind of map out what is that dependency structure and what are the kinds of usability and just the sort of classical human computer interface and programming questions, what are the real underlying analytical challenges, and those, then that will really start to compound.
Yeah. So go ahead, Dmitry.
We're also in a kind of interesting position right now with this modeling because we can actually define pretty sophisticated models right now, nested, many layers of nestedness, but running inference in all of those is not possible yet. Or again, returning to this debugging discussion, we may run inference in certain like nested models, very deep structures, but maybe they are not performing the way you would expect it to perform. So you need to identify issues again, right? And then in this kind of, so now models are even more complex. So now like the analysis is even more complex. So again, the discussion returning to like we need tooling, so even better tooling for analyzing the result of this the very, very deep nested structure, what is actually happening under the hood. Because it's like it's cool to imagine the world where, like, okay, we can download the model for video processing, but before we can create this model for video processing, we actually need to be sure that it works, or like we need to analyze it before we can build it. So yeah, we can define pretty cool models, but the way of analyzing like what is actually happening inside of it is still yeah, work in progress.
So that's the big, let's say, the pain point right now, or the problem that stops people from building, let's say, very sophisticated active inference agents with ArcInfer, the lack of debugging and analysis tools, I think. Yeah.
So you would say that that is like a high priority in being able to break the roadblock into having certain applications that you need. And if I interpret what you were saying earlier, so that's not something you get a PhD thesis on, Don. It's something that you really you need the outside community to sort of weigh in and build some of those tool sets.
Well, yeah, I mean, a community that's funded, right? But
well, that's what I mean. You're getting a
yeah,
funding around those set of goals. No, that's exactly right.
yeah.
Yeah. No, I was very early into the symbolics computer. I bought one of the first symbolics list machines, and for a company I started, and it was all about building tools. There were tools on top of tools on top of tools, and we had more tools than we had products, but and that was part of the problem. But here, I think that you need a specific set of outcomes that you're trying to achieve some kind of goal, and you want the requisite tools to do that. Do we know? Do you have a sense of specification of what those tools might be? I mean, Dmitry, maybe you say, hey, there's a bounty out here. We need this tool, and this is these 5 tools. What would those be? And
as I mentioned already, this visualization tool will be extremely helpful indeed, and be able to visualize the inference results on this visualization.
Okay, through the visualization, all of the heat.
Yeah, maybe like if everything works, you don't even need it, right? This is kind of a but when you're developing an agent, you will certainly need this. So being able to visualize a part of your model and like dive into it, and then like see what kind of beliefs were there at a particular point in time. So like maybe we can even go back in time, right, to see how the shape has changed over time, how other variables that were connected, like what kind of information did we receive, and then if we fail for whatever reason, what like before failure, we want to analyze the state of this submodel. So that's that would be.
So you're saying being able to run submodels and larger models in different contexts, and then make them independent, run how to see it, and get a trace as to why they fail, and then be able to pop it up again. That sounds like a list machine to me, but oh, okay. Well, this is great.
Yeah, but it's you want to step through it and also go back, right?
Yes,
And
yes.
pinpoint where it goes wrong, and then actually analyze the neighborhood of that graph, like who's responsible for sending the bad message, right? That's
also because actually recently we also implemented like new algorithms for approximating messages and approximating posteriors based on like exponential family projection as a very complex topic to cover in this, but it actually returning also so we want to run inference in a bigger like in larger models in a large space of models, right? So we want to introduce some sort of generic methods to run inference, and those generic methods they are not that efficient because they're generic, and also they have some hyperparameters. The idea here is that you may want to experiment with your agent with like a particular configuration of your model, and maybe at this particular point you are not really interested in running in real time. You just want to simulate your environment, and then you find the model that you think works really good, and then you start optimizing this message passing rules. You start tweaking it to make it real time, and these algorithms they help with that. But because those algorithms they have some sort of hyperparameters, they may fail as well, like approximating certain messages. So you need this kind of a mechanism. If a failure occurs, you want to understand if it's actually a model, if it's a model problem or not. Maybe it's this approximation problem. Maybe I just need to change the approximation method, or maybe I need to make some clever decisions about how we compute the messages. Without this tool, you can only guess, and then you guessed wrong, you spend some time, and then you need to start again. But if there is a tool that just says you what's wrong, it's just a big productivity boost.
In the end, it always comes down to closing the loop faster, the design loops,
Yeah, that's
right? That's
Having
that's the game.
the RxInfer model of an RxInfer programmer in the loop will be yet another fascinating example.
Mr. Fractal. Well, this is great.
Yes.
Well, I really appreciate people taking the time to meet here, and I really hope that we're able to coordinate our efforts and sort of petition the different tasks that need to be done, because I think there's something really great to be realized. I think there's consensus in this group. So
Yeah, I hope so too.
yeah, and Dan, well, the Active Inference Institute has a number of activities underway to do that. So
Yeah, fantastic. I mean, are you going to be any of you, Daniel or Andrew, in Oxford?
Some people may be in IY. Also, we'll have an online applied active symposium and probably have a RxInfer track or a mini hackathon. But I think by the end of 2024, we will have a lot of progress towards a tech tree, and we hotly follow GitHub releases of RxInfer. And I think it will be really amazing just to checkpoint year after year how many RxInfer models are out there and open source, and how do we push the frontier further and make a broader shoulder of accessibility. So it's really a great ride, and thank you all for the work you're doing.
Thank you
thank you.
for your
All right,
great
great
support
guys.
and
Thank you
Thank you.
for
Yeah,
inviting
thank you
us
so
Take
and
care.
much.
discussing.